Hello, my name is Eber Barbero. I'm your instructor for MAE 343 Intermediate Mechanics, and today I'd like to talk about Chapter 2, Materials. So in metal design, which is what we're going to do in this class, and basically this class prepares you for other courses like machine design and aircraft structures. And it basically prepares you for your professional career if you have to do anything with machines, structures, things like that, which of course you will have to do. And so in metal design, which I always emphasize metal design because this is in contrast to composite materials. Okay, composite material is the area of my area of expertise, and it's very different because metal design and composite material are different. And so one of the things that are different is that in composite material you design the structure and the material at the same time. For metal design, no. For the metal design, material selection and the design are separate tasks. And the first thing you do is you select the material. Okay, so you select the material based on properties or features that you want from the material. And if you are the only engineer in the company, then this is your job. But if you are in a big company, probably there will be experts that will help you select the material. All right, even the business people will help you select the material. So how you select the material? You select the material most important, the material property. That means you want the strongest, lightweight, most lightweight material you can find. Maybe the stiffest material you can find as well. But then, of course, there are other considerations, cost, of course, manufacturability, because you can pick a very high strength steel that then nobody can weld, and the guys at the shop are going to complain. So this is an issue that will be considered at the onset, at the beginning of the project. Then, of course, durability meaning corrosion, things like that, mostly corrosion, because other durability issues like fatigue enter into the design. But here at this stage, what we're talking about is durability, brittleness if you do polymers, stuff like that. I say metal design, but when I say metal design, I mean anything that is isotropic. Isotropic means that the properties of the material, what properties? Well, the modular elasticity, you know modular elasticity, E, right? The tensile strength, that's kind of obvious, is independent of the orientation. So if you look at any of these parts, let's say this gear, in this direction, if you go from here to here, the modular elasticity is 1. And in this direction, from here to here, the modular elasticity is exactly the same. And along the teeth here, the modular elasticity is exactly the same. The strength is exactly the same. This means this material is isotropic, of course. If this was a composite material, that will not be the case. All right? And so durability, and then end of life, that means recycling. When the structure, part, component, device, whatever you want to call it, reaches its end of life, and the car is too old, not worth to fix it, you throw it away, what are you going to do with it? You have to plan for it, all right? So once this is done, the material is selected. That means that the properties are fixed. You cannot change them. They're absolutely fixed. And then we go into really what we call the design, all right? So the design is only the design of the geometry. There is nothing else that you can change. And why you design, how are you going to design the geometry? Well, to get strength that you need, to get the low weight that you need, and to get durability, but this different type of durability, no corrosion. Here we're going to talk about fatigue, all right, in this class. And then if when you try to design, what you come up with is too heavy, too big, or doesn't meet the fatigue resistance criteria, then you may have to go back and reselect the material. But that is unlikely because materials, you don't have a continuous spectrum of material properties. The material properties jump. From aluminum you go to steel. Aluminum is low modulus, steel is high. In the middle there is basically nothing. So we are very reluctant once you select the material to change it. Okay, maybe you change the alloy, you change the thermal treatment, but these things are not material selection. Okay, this is more like manufacturing. All right. So okay, so in this lecture we're going to talk about material properties. All right. So then we can do the design because we need to know these material properties that affect the design. Okay. So there we go. So we got an outline. And today we're going to talk about the tensile test, and we're going to talk about engineering versus true stress and strain. So this is something probably new for you. What is this true stress, true strain? Then identification mode of elasticity, you know about this, and we're going to pay attention to identification of yield. Identification means what is it on the stress-strain diagram and what it means, and how do I get it if I had to do a test. So yield, ultimate stress, and failure stress. Okay, so let's go into it. All right, so the tensile test. So mechanical design requires a lot of material property. You'll see when we start cranking up equation that you want this, you want that, you need this, you need that. Okay, so if the properties is to measure in the lab with a machine in testing, and if we can do the test cheaply and fast, and we can do that, or most likely, if the test is cheap and fast, somebody already did it. And the data is available, great. Then we don't have to do anything. We just look up the data and we move forward. That's what we want. We are the structural engineer. We are the analyst. We are doing the design, and we don't want to waste time with that, okay? So now, but if the test for the material property that we need is difficult, expensive, time-consuming, well, it will be hard to find such data because people are reluctant to spend money. So what we want is we want to do as much as possible. What do I mean by do in the design? If we can design everything with data that is available, great. Okay, and the data that is available is the data that comes from a test that is cheap and fast. And this test is the tensile test. All right, tensile test is very simple. Now, to know what the tensile test is, you can take MAE 244, which is the lab, and I hope that everybody already took this. Or you can watch this video, not or, even if you took MAE 244, I want you to watch this video, because, you know, watching this video, it gives you, don't you remember the video, and it gives you a good idea what I'm talking about, okay? And here's the link, and if you don't watch this video, I mean, I'm not going to ask questions about the video, okay? Like I could ask, but no, what it means is that then when I say things later on, you're not going to understand what I'm saying. And so you're going to miss out on details about what I mean because you don't have this same background that I have. So I watch the video, and when I'm going to say something, I remember that, and I put that in context of that video. You don't watch the video, then you don't know what I'm talking about. All right, so the specimen for the tensile test could be cylindrical or not, or squarish, but for metals, since the material is isotropic, it's easier to do cylindrical. Why? Because you do it on a lathe. You see, I bring manufacturing issues into the picture because I have background. I can run a lathe, I can run anything, weld, whatever. You name it. So, okay, so then on a lathe it's easy. You put a chunk of steel and then you can, cut this piece down here until you get the diameter and over the gauge length. And so what is this? Why you have to do this? Well, you do this because in this region, thick region, to apply the load, you're going to put it on a machine and you're going to grip it with the grips. And the grips are going to put compression stress in this direction, and so there's going to be all kind of stress concentration. And by the way, we have a topic that is a stress concentration later on in this class. And so to avoid the stress concentration from measuring our measurements, which our measurement will be based on P over A, and we're going to talk more about this P over A. To calculate the stress, we do P over A. But that is only true when the only stress is in this direction, in the direction of X, along the length. And for that to happen, we have to be away from a stress concentration. So we reduce the diameter and we make this this shoulder here very smooth and with a large diameter. All these things we will discuss in this class. Why it has to be large radius, this shoulder. And we reduce the cross-section so that the compression stress here will be low because the cross-section is big. And then we reduce even further with this shoulder, and then we go away and we say we're not going to measure anything here because it's too close to the stress concentration. All these things we're going to discuss in this class. And so then over here, I am far from the stress concentration, so the stress should be P over A, the load divided by the cross-sectional area. And I measure it over that gauge length. And if you watch the video, you'll see that the guy there uses an extensometer, and the extensometer clips here and it clips here on the gauge length. So the extensometer will measure the elongation, that will be the change of length. The computer will calculate the strain. You have the, because it has diameter, you enter the diameter. Well, you enter the diameter, the load, it will measure the load, and you have the diameter, you can calculate the stress, and then you can do the stress strain plot. Okay? So, watch the video. All right. So, okay, so then this picture comes out from the video, but the data, no. The data I took from another paper or report that I got from another university that I thought they did a very nice job. So what they did is they did similar tests for AISI, that means American Iron and Steel Institute. 1020 is like a classification, is a low carbon steel that is very ductile. And then hot rolled steel. And why hot roll? Well, because the way it's manufactured, it changes the properties. All right, so you will have to be aware that it's not the same 1020 hot roll and cast or cold drawn, for example. No, it's different. They will have different properties, especially the strength. The modulus, no, modulus is a material property that is typical of steel, and there is pretty much nothing you can do about it. It's pretty constant. So, okay. So what I do is, okay, first I measure the initial length of the specimen 50. That will be this will be initial length, the gauge length. So the gauge length, which will be maybe from this to this, I forget. I haven't seen the video for a while, I confess. So, okay, so the gauge length is this, 50. But by the end of the test, you see how it grows like that? Okay, it stretches, and then when it breaks, which it breaks here, it remains stretches. So it's almost like a rubber band. It grew from here to here, and this is a steel, all right? And so the final length is 70, initial diameter is 911. This is the diameter here, initial. And then final diameter is 520Y8, but there, in this region, where we have what we call necking. And during the test, they record the force, P in kilonewtons, and I'm sure they measure in pounds, but then they convert it because all these decimals. And then the engineering strain is calculated from the elongation and is given here. Engineering strain, well, we'll see what engineering strain means. And then the diameter, which is measured at the beginning, and then they measure when this necking occurs over here. In the video, they don't measure the diameter because you gotta basically put a different instrumentation to see this diameter when this is happening. And because of this change of instrumentation is that this area is blank because the change in diameter was not great. Here at the beginning, no change, no change, no change. And over here, probably changed a little bit because you gotta get from 9 to 7, right? So somewhere it changed, but they didn't notice it. So at the end, they measure only when it counts. That is when it's very, very large. And I'm going to give you a homework to analyze this data, and you will tell me when it's worth to use one formula or another, when this change in diameter is important or not. Okay, so then we have the data. This is what we get from the lab. We pay, they send us this. And then we put it in Excel. I put it in Excel. And then this is the plot. So it goes up to a maximum, then it's a little bit deep, then there is this wiggly here portion, then it goes up again, all right, but with a lot of less modulus, because modular elasticity is the slope of this curve that cannot be seen in this plot. And then, but less modulus, then it has a maximum, and then it goes down, and it fades. So this plot has two problems. One is that the important region, which is from here to here, which is the elastic region, that's the region that is useful. All right. After that, we crash the car, and yeah, okay, we need this region to see if the crashworthiness is good or bad, if it's going to kill people or not. But but we try that people do not crash the car. Basically, we design everything so that it will not be plastic deformation up to this point. And in this plot, we cannot see what's going on here because the strain at failure is so huge, almost 0.4. This is tremendously large. You can see here, is a strain so large that then this plot is bunched up here. But this is easy to solve. Now, the other thing interesting or not nice about this plot is that how come that the specimen fails when the stress is lower than the maximum? This seems strange. Okay, let's investigate. Okay, so first thing we do is we label this plot. All right, so then we got S of y is the yield strength, which I put here, not there at this peak. Okay, then SUT is the maximum value ultimate, U is for ultimate, that's the strength. Is the maximum value of stress that I can put, but what type of stress? Engineering stress. And then it go down to SF, which is the engineering stress at failure, all right? But for design, we use this value because the only stress that we can calculate for design is the engineering stress. And so we cannot let it be more than this because that's the maximum, all right? So in order to get the model elasticity, what we do is we magnify this. So this goes from 0 to 0.4. Okay, so we magnify, we take only this part of the Excel plot that goes from 0 to 0.01, all right? So that will be 10 times less than this. So somewhere here. And so we see that, okay, further is this line that goes here. This is Hooke's law, sigma E times epsilon. This sigma is P over A, when A is the initial area. What the initial area? The initial area that I calculate with the initial diameter. All right. And E times epsilon. Epsilon is the engineering strain, which is delta L over L. What L? The L sub 0. Okay. That means delta L divided by the initial length, which is this, not this. All right. Okay. So now this point over here is very difficult to catch. Okay. Things happen very fast, and not all metals have this. In fact, only low carbon steels have this dip that it goes down. Most materials, they will remain like that and stay here or go immediately start to go up. So since this is so variable and it's difficult to measure, okay, these guys measure it because they are at university. I forget the university, what university was, but they have good instrumentation like I have here at WU, and we could do this. But from day to day, you're not going to do this. A normal lab, which you can have even on inside your shop, not going to do such a fancy job. So it's difficult to catch. So it's normalized. Okay, people agree and it's standardized. They say, okay, no, you go to 0.002, which is 0.2%, that's a very small strain, permanent deformation, and then you draw a line red parallel to this line, and when it intersects the data, that's your S of y, okay? And that's the way it is defined, all right? And the fact that the material can take a little bit more, okay, use it as a safety factor. It doesn't matter. We're not going to use it. Now, why this line and this line are parallel? Well, they're parallel because if you load the material on this line, the material is elastic. And if you change your mind and you say, no, I want to let the load go, then you go back here to 0. You have no permanent deformation, okay? Imagine the shopping cart hits the side of your car. And it was coming very slow, so it bounces back, and you go there, and there is no problem. It didn't dent the door. Great. Now, here comes another full shopping cart that is coming from far away on a West Virginia parking lot that always have slope, significant slope. And so it goes with high speed, it goes up, and then it goes like this, and it goes like that, because the material cannot go here, right? So it gotta go that. So that means that you start to accumulate a dent in your car. That means you gotta talk to the insurance or what. So, okay, so now you got a dent in your car, and here the cart stops, all right, it bounces out from the car. That means that the load disappears. So what the material is going to do, the material is never going to go back like this. No way. Now it's bent. Now what the material is going to go is going to come down with a slope same as the original. Modular elasticity did not change. That means plasticity doesn't change the modulo elasticity. So it's going to come down with E, this modulo elasticity, and it's going to come down, but it's never going to get to 0 because now the door of the car is dented, and this is the dent. Hopefully this is a very small dent and you can live with it. All right, leave it like that. All right, so this is the way it's done. You do this test, then you put 0.002, draw a line parallel to this, go up, and when you find this number, this is S sub y, and this is the yield strength. It's a value of stress, but it's a very particular value of stress. That means that is when we say the material yielded. Forget the fact that it yielded here. We say it yields there, and that's what we're going to use for the design, okay? So, all right, how do we get the modulo elasticity so that we can draw the parallel line? Well, we magnify even more. That means we take only the data points that we have along this line, which are these data points. From the table, I took those points, and I put them in Excel, and you do a linear regression. You have to learn to do this if you don't know already. Do a linear regression, tell Excel to write the equation there, and that's E. 201.171 megapascals. Why megapascal? Because the diameter is in millimeters, so the area is millimeter square, and the force is in Newton. Well, here it says kilonewton, but you gotta put it in newtons because Newton per millimeter square is megapascal. So this is megapascals. Okay, so all right, so then we got that. So we have modulo elasticity taken care of. If I give you the data, you can tell me what the modulo elasticity is. Exactly. No, you don't need partial credit for this, right? So okay. So then now let's talk about this business about going down here. Okay. So this picture you already seen what's going on. When this happens in this region. All right. So here you got plasticity but no necking. All right. And then after this point you have necking. Yes. So the problem is this. When you calculate this stress, which is the blue line, you do P divided by A sub 0. A sub 0 is the area of this bar. And it's the only area that the designer knows because when the car is crashing, you're not going to go measure the area. You don't know what this area is going to be, all right? Now, this area could be calculated. Yes, I could reproduce this plot and calculate the true area using sophisticated finite element analysis, not just something cheap. But no, nobody's going to do that, right? Nobody's going to do that. So the designer is going to say the area of this is, I don't know, 3/8. And so, okay, diameter. So pi diameter squared divided by 4, that's my area. That's A sub 0. That I know. You tell me the law divided by this, I give you the stress. And everything is fine until the area starts to reduce, because diameter starts to reduce, area starts to reduce. If the area starts to reduce, then it's in the denominator, the stress is going to shoot. And so that becomes true stress. True stress is sigma P over A. What A? The real A, which will be this A. And if this A go down, okay, even if the P is not growing, if the A go down, the stress is going to shoot, and you can see the plot, it shoots. And it shoots to 800. Well, this was only 400 at the peak. All right? Okay, when do you need this? For crashworthiness. That's the best example, both for the aerospace, aircraft guys, and for the mechanical car guys. All right? If you have a hard landing and you want to design the landing gear, okay, this is the curve you want. All right? This is the material you want. All right? Tough material, very large stress, very large deformation. It doesn't break. It bends, but it doesn't break. So this will be true stress defined. All right, now you know what it is. Okay, and now true strain is a little bit trickier to define because okay, the engineering strain from MAE from the sophomore mechanics of material is delta L over L0. Usually they put L in the books and they don't say anything, but it's the L you know. What do you mean the L you know? Well, when you do the design, you say, okay, this is going to be 10 inches. Right? Because I say so. I'm the designer, I say 10 inches. So L is 10 inches, but that I call it L0 because that means the initial length. When things start to deform, L0 no more. I mean, I gotta have L, the real L, which will be, you see, when this is stretched to L. So the true strain is not this formula, but this more sophisticated formula from calculus. it says that the differential strain is the differential length. That means at every point, how much is the stretch divided by the length at that particular point. That means if I want to stretch this a little bit more, well, now it's broken, but just before it broke, I could stretch it a little bit and calculate delta L divided by what L? The real, not the original, the real length. And that will give me the true strain. But I don't have the function L as a function of time to calculate these differentials. So I gotta derive a formula, and that's why I say it's trickier, but we will do this in the next video. And so we can plot true strain versus true stress. All right, so, okay, so far what we have learned. Modular elasticity that you knew what it is, but okay, now I'm doing a little bit of how to calculate. Yield strength, and now we define exactly what we mean by it. And this is probably the most important parameter for the design in this class and in machine design and probably in aircraft structure as well. If it's metal, if the plane is metal. If the plane is composite, no, that's another story. Ultimate strength, SU, which could be T if it's tensile or C compression. We will talk about this also in the video number 3 a little bit, and then again later. Metals, when they are annealed is there is no residual stress inside. That means once you stretch a metal during manufacturing and you make a bar, you have an ingot, and then you stretch it to make a rod. Okay, the rod cools down kind of fast because they leave it there at room temperature, and it cools down, so it has residual stresses, and it's not truly isotropic, so it has a little bit different tensile and compression strength. So if you want a true nice isotropic material, then you have to anneal it. That means you heat it up to a certain temperature, and then you turn down the oven slowly, and all the residual stress go away. And in that case, metals have SUT equal to SUC. But cold worked, strength hardened materials don't. Next video, we talk about this in next video. So then you know what necking is. Resiliency, we've seen resiliency. Let's review resiliency. Resiliency is the area of this. You draw this line vertical to this sort of yield point, not exactly, but oh well. And then this line. So when it goes up like this, the material is stretching like a rubber band, and it's accumulating strain energy. And then all the energy that the material can accumulate without permanent deformation, without going down this way, is called resiliency. So resiliency means that is the energy that you can take from the shopping car. The door of your car can take so much energy from a shopping car without noticing. That means if you don't see that somebody bumped the shopping car against your car, you don't know what happened, right? And so this will be resiliency. So from that point of view, for cars, resiliency is good. In fact, at one point, GM had a minivan with fiber reinforced composite doors precisely for this reason, and they had a lot of advertisement. This was a long time ago. So they put a lot of advertisement about this, that okay, the shopping car will bounce full of groceries and it will bounce back, and the minivan was cool, no problem, no dent, okay? And all the other minivans, they were trash. Anyway, so this is resiliency, no damage, all right? If it is resilient, no damage. And toughness is the area under this curve. And so that means that the area under this curve is energy, because stress multiplied by strain is energy per unit volume. Okay, we'll talk about that later. But anyway, so the area under this curve is energy per unit volume. So per unit volume, this material is very tough because it can suck up a lot of energy, and without failing. If you get here, it actually fails, and you have seen how it fails. It fails like this. All right, so when you go, it fails like that. But if you got to this point, it still didn't fail, and all this energy is huge because you see it's so spread, go to almost 0.4. Okay, I hope you appreciate that. All right, so okay, so we got resiliency, we got toughness, true stress. Now you know what it is and how to calculate. True strain, you know what it is, but you don't know how to calculate because the differentials. But in next video, we will derive these equations. So that's what we do. Equation in next video we have equations for true stress, true strain, resiliency, toughness, and ductility. And with that, this is video number 1 of materials, chapter 2. Thank you very much.